Hello, this presentation will discuss how normals change under affine transformations. You can find the material in section 4.4 of the PDF online. Their setting is the following. A point X lies on a surface S with a normal vector n at the surface at X. So the picture is something like the following. Here's the surface S. On this surface there's a point X, and there's a normal vector n at right angles to the surface right there. And an affine transformation, A, mapping R3 to R3, sends S to A of S. We transform the surface, X to A of X. That's the transformation of the point. And the question is, what is the normal M at X at A of X on A of S? So our picture here is that the transformation A has sent the surface someplace else in space. X is still on the surface, so here's A of X. It's got a normal vector M here. And we don't require them to be unit vectors. We're not particularly concerned about the length of the vectors here because we can always normalize them. But we want to know the direction of the normal vector M on the transformed surface. And we'll want to see what happens here. So first of all, first comment is that if A of X as a linear as an affine transformation is equal to B of X plus U, where B is linear, so remember, an affine transformation is the linear transformation plus a translation. So we take B as linear, then M depends only on B, not on U. And this is because if we do a translation, it just shifts everything around without changing their size or shape or orientation. In particular, the normals don't change at all when we do a translation. So if we translate by U, it doesn't change the normal. So without loss of generality, A is just linear. In other words, U is 0. Right, so let's just henceforth assume A is linear. And of course this means that then A is represented by a 3x3 matrix. And this is a 3x3 matrix operating on XYZ coordinates in R3, not operating on homogeneous coordinates, operating on ordinary coordinates in R3. So we'll see that we don't get M just by applying A to N. So the normals do not transform by the same linear map A as the surface does. So let's do an example of this in R2 for simplicity, and then we'll get to the general formula. Here is an example in R2 showing how normals do not transform as expected. We'll let the surface be a line segment, and in particular let's let it just be the line with slope -1 that joins the 2 points 1, 0, and 0, 1 with a line segment. So S is this line segment here. It has its slope is -1. X is in the middle. of that line segment, so it's equal to 1/2, 1/2. And our transformation, A, will be S 1/2, 1. So it's scaling by the x-coordinate by 1/2 and the y-coordinate by 1. And so if we transform by A, the surface S becomes the following. It's now joining the point 0, 1 to the point 1/2, 0. So here's A of S. It takes the point X to 1/4, 1/2, the midpoint on that line segment. And what about the normals? So the normals, the original normal here, n, it could be taken, for instance, to be 1, 1, because it's got slope 1, and that's at right angles to slope -1 surface. We could use also square root of 2 over 2, comma square root of 2 over 2 if we wanted the unit vector, but again, we don't really care that much about unit vectors here. So what's the slope of the image of A of S? This is slope -2. So if we take a normal vector, which I'll call M, to A of S, and let me fix this earlier typo here. This was A of X was the point 1/4, 1/2. So if we take normal vector M, this should have slope 1/2, because that's at right angles to a line of slope -2. So we could take, for instance, M to be 2, 1, for instance, because that's a vector with slope 1/2. So is M equal to A of n? No. So M is not equal to A of n. A of n would be 1/2, 1, which would be sloping with slope 2, not slope 1/2. It's almost like the following, but not quite. It's almost like M equals A inverse of M. But this is not correct in general. It does work in this particular case, but it's not correct in general. The correct way to find M we have that A is represented by the 2 by 2 matrix M, which is 1/2, 0, 0, 1, and then the normal vector N is equal to M transpose inverse times N, and that's the same as M inverse transpose times N. It's easy to check the fact that M transpose inverse is the same as M inverse transpose. It's easy to check. You've hopefully seen that in a linear algebra class before. And this is the formula that we use to get a vector normal to the surface A of S at the point A of X. And we'll prove this in general in the next couple of boards. So let's state the theorem for the general case going back to R3. Let A mapping R3 to R3 be linear and invertible and represented by the matrix M. So M in particular is also invertible as a matrix. Let X be a point on a planar surface, actually a plane is the same thing, planar surface S with normal N. So it's enough to prove the theorem for planar surfaces instead of general surfaces because we're assuming these surfaces are well formed and smooth, and we can just replace S by the tangent plane to S at the point X. And if we get a normal to the tangent plane, then we also get a normal to the surface. So that's not too hard to see that this respects transformations by linear maps as well. Okay, so then if you form M in the following way, M equal to M, capital M, inverse transpose of N, which is the same as M transpose inverse of N, is normal to A of S at A of X. And again, with our assumption that it's a plane, it doesn't matter where it is, but I'm just going to keep stating it in the more general setting. And just making the assumption of planar for simplicity in the proof. So for the proof, we have this key property of normal vectors for surfaces. So if I've got my surface here, S, and a point X on it, and a normal N, the key property here is if you take any tangent vector T, I mean tangent to S at X, then the key property is that T dot N equals 0 for any T tangent to S at X. Right. And likewise for M, we have that U dot M equals 0 for any U tangent to S, A of S at A of X. So just to draw the picture here, here was S, maybe here is A of S, here's A of X lying on the plane, here's the normal vector M that we're giving the formula for, and if I have a tangent vector U tangent to the surface, then M dot U equals 0. And this is the defining property for our normals. If these properties hold, then N is normal to S and M is normal to A of S. So these are exactly equivalent. And the point here is that if U is tangent, well, let me call this a claim here. If U is tangent to A of S at A of X, then U equals A of T for some T tangent to S at X. And the proof of this, I'll be maybe a little hand wavy on this, but it's pretty much accurate here. In fact, it's easy to make it rigorous, is as a tangent vector, U is a difference of 2 points. So there's some point X, there's A of X, and there's some point V. And if the surface is planar, then we can just take V to be on the surface. If the surface is not planar, we would just be taking V's arbitrarily close to A of X and taking some sort of limit process. But let's just assume that the thing is planar, so this actually lies on S. Well then, A inverse, we let, so in particular U then is equal to V minus A of X. Well, with the planar surface here, here is A inverse of V, right? So then we just take T to be A inverse of V minus X. And with the assumption that the surface is planar, A inverse of V lies in the surface, and this lies in the surface, or at least is tangent to the surface in the general case. Lies into the surface, S, if planar, or is tangent to the surface in the general case. In the general case, you get this tangency by taking limits as V gets very close to A of X, and then A inverse of V would get very close to X. Okay. So this claim will be very helpful for proving the theorem, which we'll do on the next board. Now we need to prove that U dot M equals 0 for any U tangent to A of S at A of X. So we know that that U is equal to A of T, which is the same as M times T, for some T tangent to S at X. And M is equal to M transpose inverse times N. Now we have that U dot M is equal to MT dot M transpose inverse times N, using the definition of M and the formula here for U in terms of T, and that's equal to MT transpose times M transpose inverse times N. And here what I'm using, this is matrix product now. This was dot product. This is now matrix product. And we're using here the fact that if you have general vectors A and B, that A dot B equals A transpose B, where we think of A and B as being, A transpose as being a 1×3 matrix and B being a 3×1 matrix. So we just took this and changed it to its transpose and replaced the dot product by a matrix product. So that's equal to T transpose M transpose inverse N, using the fact that a transpose of a product is the product of the transposed objects in the opposite order, and also using associativity to drop parentheses. So we can group these things together by associativity. And this gives us T transpose N. Okay, and that is T dot N, again by the fact that A transpose B equals A dot B. And that equals to 0 by the choice of, by the fact T is tangent to S and N is normal to S, both at X. And that's the theorem. We just showed that u dot m equals 0 for any u tangent to a of s at a of x. That's the end of this presentation. Thank you very much.